I just realized I need to record this. All right, let's talk about what these Pythagorean triples are all about, what they mean. Most of you guys know, my husband, who knows no math whatsoever, can spew out a squared plus b squared equals c squared, right? You guys, when you hear Pythagorean theorem, that's what you think of. But really, my preference is that you think of that as leg squared plus leg squared is equal to hypotenuse squared. Because A and B and C might be labeled a little bit differently in different triangles. Kind of a default setting is that C is the right angle in right triangles, but it's not always the case, so just be conscious of that, please, right? Be careful with that. Pythagorean triples, if you can get these memorized, they are a time saver. They save you a little bit of time and effort and energy, basically, okay? The first two numbers would be the lengths of the legs of a right triangle. The last number, if you notice in every set there, the last number is always the largest. So that's representing the hypotenuse, okay? So here's how this works. Here's how you use these. Come on. There we go. Maybe. Here we go. All right, if you are given a right triangle, and you are told that one of the legs has a length of 4 and the hypotenuse has a length of 5, then without doing any work, you should know, if you've gotten them memorized, that the length of this leg has to be 3. Now the beauty of this is that until you get them memorized, or if you don't notice that something is a Pythagorean triple, you can always do the work and say 5 squared minus 4 squared is equal to whatever, and take the square root and get your answer. So fallback is Pythagorean theorem, but it's so much faster and easier if you can think about these triples because you see them so often. On your Delta math assignment that you had, I'm trying to remember now. It seems like my recollection is that one of the sides was 35 and one of the sides was 21, and you were supposed to do and you were supposed to, you had to figure out the other side and then do a trig ratio for that one, right? Okay, that's a 3, 4, 5 right triangle. It's just that all of the sides are getting multiplied, right? This is 3 times 7. This is 5 times 7. So to figure out what this side is, you know it has to be a 4. It has to be a 3, 4, 5 triangle. It's just that it's getting multiplied by 7. So yes, this side max would be 28. Okay? All right, good. So that's a triple. What would y be equal to? Who said that? Aiden, was that you? 10. You are right. No thinking needed. He just knew that. Tell me what the triple is. Okay, this is a 5, 12, 13 triangle. Right? Each of these values was multiplied by 2. So 5 times 2 to get the 10. Right? So that was a 5, 12, 13. You see that, I hope? Yes? No? Maybe? Okay, what about this one? What is z equal to? Nice! And you did that in your head. Booyah! Nice, Jaden. Okay, what's the triple?
8, 15, 17.
Good. This is an 8, 15, 17. This is 8 times 3 is 24. 15 times 3 gives us 45. 17 times 3 is equal to 51. 51, everybody always gets tricked up on that one because everybody always thinks that's a prime number, but it's not.
What's 51?
51 does
Which one's a prime number?
No, people think that 51 is prime, but it isn't because 17 times 3 is... Okay. All right. Another reminder. I'm going to ask you to refer back to your... I'm going to ask you to refer back to your geometry days a lot over the next semester. I need you to recall and remember, angles are represented by uppercase letters. So this is representing this angle up here that uppercase A is saying that's angle A of this right triangle. I did put C as the right angle here, and this is angle B. You need to remember that the side opposite the angle, there's that connection there. So angle A, if we draw and go across or opposite that angle, that is where side A is. And side A is represented by a lowercase letter, right? So opposite angle B is where side B is, and it's going to be a lowercase b. And then opposite the right angle would be lowercase c, right? Okay, another way these sides could be represented besides that one little lowercase letter, side C could also be written as AB, basically saying segment AB. Side B could be also written as segment AC, and so on, right? So think about different ways that these sides and angles can be written or represented. So just be careful with that. Notation is gonna be important. Okay. We just have to kind of review a little bit of vocabulary and then a few concepts here. Okay, acute angles, what do we know about acute angles? Less than 90 degrees, good. And right angles, think corner. You may or may not see that little square. So right, they are exactly equal to 90 degrees. Obtuse is greater than 90 degrees. And then a straight angle, how many degrees is that? 180, there you go, good, right? Think about how a straight angle is formed. We start at a particular location, we rotate around so that we are drawing straight line, even though that's not real straight. You know what I'm trying to draw there. Okay, complementary angles, they add to how many degrees? Oops, careful, complementary, C comes before S. So 90, and 90 comes before 180, so yeah. Complementary angles, the sum is equal to 90 degrees, and for supplementary angles, the sum is 180 degrees. All right, so yeah, if we want to find the complement of 32 degrees, what are we going to do there? Subtract what? Subtract 32 from 90. So 90 minus 32. So the complement of 32 degrees is 58 degrees. Find the supplement of 110 degrees. That means we're doing 180 minus 110. I'm bad about remembering the little degree symbols, so let me go back. Okay. Everyone's favorite thing, word problems. Let's look at these examples.
Oh, I can do this one.
You can? Okay.
You gotta do this.
So it says one angle of a complementary pair, so that would be equal to 90 degrees.
Okay. So
that's
we
equal
have
to 90.
two things adding together to 90. That sounds good. And then what?
And it's 3 more than twice the other, so it would be 3 plus 2x
Okay.
plus x.
Good. The key is remembering, guys, the key is remembering this other x. That's what most people forget. They get the 3 plus 2x, but they forget to add the other x. So just be careful with that, right? All right, and then we're just doing some basic math here. So 4x,
Wait, wouldn't it be 3x?
I'm sorry, 3x. Yep, sorry. Checking to see if you were awake. Okay, so 3x is 87. So x is, what, 29 degrees. We're supposed to find both angle measures. My suggestion when you're doing this, actually plug the 29 into this 3 plus 2x. So 29 times 2 is 58 plus 3 is 61. If you plug in there, then when you get these answers, then you can kind of, as a check, you can add those together and see that you're getting 90. If you just go straight from 29 and say 90 minus 29 is 61, then you can't really check to make sure you haven't made a careless mistake. So, for what it's worth. All right, so who's got this next one?
I can do it again if you want.
Okay, go ahead, Davis.
So,
Yeah, do it again.
one angle of a supplementary pair,
Mm-hmm.
that's 180.
Okay.
And then 15 less than 3 times the first angle, 15 minus 3x.
Okay, careful. It's 15 less than that. So we got to switch that order. So just be careful there. So it's going to be 3x minus 15, not 15 minus 3x,
You better
right?
put your
So
head that way.
be careful.
You better turn
So keep going, Davis. You're doing fine.
plus x.
Plus x. Okay. Here we get 4x minus 15 is equal to 180. Okay, we're dividing by 4. I'm trying to remember what we get. It's a decimal.
48.75.
Okay, thank you. I thought that's what it was, but I couldn't remember. Okay, so for the one angle ends up being 48.75. The other one is 131.25 degrees.
Davis? Davis, you got the next one?
Oh, God.
0.25 degrees.
I'll try it.
Okay, we're gonna talk standard position here. I need to refresh your memory about a couple of things that you may or may not remember that I want you to remember. First is, how do we label our quadrants?
1, 2, 3, 4.
Okay, think of it kind of as a C. We start top right, so quadrant 1. Please make sure you are using Roman numerals. If you're not using Roman numerals when you're labeling a quadrant, I'm probably going to mark it wrong, so just be aware of that, okay? Okay, so there's quadrants 1, 2, 3, 4. We're going to use some terminology here that I need to make sure you're familiar with. If you notice, this is saying an angle in standard position is said to lie in the quadrant in which its terminal side lies. You're going to see a lot of problems and examples where they're talking about the terminal side. So I need you to think about what that means. When we create an angle, we are starting with a ray, and we're going to talk about the fact that it's in standard position in just a second. But we start with a ray, and then we rotate. So the starting place, that's our initial side, right? We start somewhere, we have this ray, that's our initial side, and then we rotate, and wherever we stop, guys, hopefully that should make sense, that's our terminal side. Terminal means stop, right? So this is our terminal side. So, yep, when we start to create an angle, we are going to start at a position that's our initial side, and then we rotate, and wherever we stop is our terminal side. Okay? All right, so an angle is in standard position if the vertex is at the origin, and then the initial side lies along the positive x-axis. So you guys saw that yesterday on your Delta Math assignment that you did. All of those, it started here, right? We had a ray there, and then you were asked to do the rotation. All right, great end. So let's think about what this is saying. An angle in standard position is said to lie in the quadrant in which its terminal side lies. So we start in standard position. We start with this ray in standard position along the positive x-axis. And if we say that we have an angle in quadrant 3, then we know we are rotating around and we are stopping so that our angle is somewhere, that terminal side, that ending location is in quadrant 3 somewhere. So what would the angle measures be? Has to be greater than what and less than what? Oh, careful. If we're in quadrant 3, because if we rotate to here, we're at 180.
So greater than 180.
So good, there you go. You were on the right track, Armand, but we're a little bit farther beyond that. So greater than 180 and less than 270. There we go. Now, Armand, what you were saying, if we start initial standard position and we rotate to get to quadrant 2, somewhere in quadrant 2, then there is where we are greater than 90 and less than 180. Good question. If we're talking about a positive angle measure, we're rotating counterclockwise.
So the negative?
If we're rotating clockwise, then it is a negative angle measure. So more often than not, you will see some negative angle measures, but most of what you're going to see will be positive angle measures.
Are negative angles possible? Like,
It was
I did not do it. Here.
All right, if we're stopping in quadrant 4, what are our possible angle measures? Greater than
270.
270, less than 360. Beautiful. Okay. All right, questions, comments? If you guys feel like you need to make a little note over here about quadrant 1 and what the angle measures would be for that, then please do that. I think you should know or understand that, but if you feel like you need that written out, then do that. Okay, the verbiage is not the greatest, but if you look at the very top box here, on the left-hand side is a term. On the right-hand side is kind of a definition or an explanation about those things. So let's match these up. So for vertex, which one of these corresponds to a vertex? Yeah, the fixed endpoint. What about the initial side? That would be the fixed ray, and terminal side is that ray that rotates. Okay, Max, this is what you were just asking about. The measure of an angle. So we get direction and how much rotation. So you were asking about the positive angle and a negative angle. So direction is important and the how much or the amount. So positive angles rotate counterclockwise. And if that's confusing for you, then draw a little picture. Right? That means if we're starting in standard position, we're starting here and we're going that way. Negative angles just mean we're starting in standard position and we are rotating that way. So that is, yikes, let me keep it, okay, clockwise. All right, somebody in their own words explain what standard position means, please. Position that what? What does it
Position
mean
that's
for
standard.
position
That's
that's
what she said.
standard? Oh, okay. Position that is standard, okay. Yes, that's true, but more specifically,
Vertex that is at the origin.
okay.
What's the origin? Just move on.
Where's the origin? You know where the origin
The
is.
original origin?
What does it mean?
Yes.
Angle
The OG
to
origin.
stand
Aiden.
position.
Ray that
Whoa, did you pull that
is
up?
on
Brain or what?
positive x-axis. And what are we doing with that ray? We're going to rotate to some ending position. Used to rotate to create an angle. Something to that effect. Sounds good. Thanks, Aiden. angle. I'm trying to write and talk, it's not working.
Wait, what?
Ray that is on the positive x-axis, and then maybe make a note. It's used to rotate to create an angle. That says create, it just doesn't look like it.
Why does it have to be on the positive x-axis?
That's what makes it standard position, is that location. That's important.
You know it's National Curry Day.
Curry Day?
Chicken curry.
I hope they don't hurry.
They don't have curry. They don't have curry?
Okay,
Chicken curry.
Actually do a good job of chicken.
I wonder if they can make me a meatball sandwich.
I don't think they can.
all right. Another term to be familiar with, become familiar with, is what's referred to as a quadrantal angle. It sounds weird, quadrantal angle. Think about the fact that it's got quadrant in it, so keep that in mind when you're thinking about this. Quadrantal is how that's pronounced. So notice what it says. A quadrantal angle is an angle in standard position whose terminal ray lies along one of the axes. In other words, we start in standard position and then we rotate, and where it stops, it's stopping either on the x-axis or the y-axis. Okay, so let's draw some pictures. That's why we've got the little grids there.
I have one like
Have you ever heard of sinusitis?
Oh yeah.
sinusitis.
And a deviated septum.
I ended up having to have surgery for that. Yeah.
I got on it too. Is it painful?
It's from allergies. No, but like once I had the surgery, things were great. Let me pause this. They don't need to hear all of this. Okay, as soon as he gets back. All right, so, sorry. All right, quadrantal angles, think about this. Standard position, we rotate and we stop right there on the positive y-axis. So we're at 90 degrees. So 90 degrees is considered a quadrantal angle. Right? If we rotate all the way around to here, so that means 180 degrees is a quadrantal angle. You're right. That's where we're headed, Braden. Not initially. We got to stop here also. 270 degrees. If we're going all the way around, actually there's two ways to think about this. There's multiple, but we might not rotate at all. Then we would say we're at 0 degrees. Or we could rotate all the way around, do one whole rotation. Then we would say that's 360 degrees. Right?
Would it be negative because it's going,
I rotated in the positive direction. You can go negative, but all right. I know.
I know attention everywhere.
That's what I was
I never was taught how to hold it right.
How do you
Well,
write
but
like that?
Like this is
that's
what's
just it. Is
comfortable.
that that's what you need to do is what's comfortable. If you watch, everybody holds their pencils differently.
I can't write with this.
Nobody, there's no quote unquote right way. Okay. All right, grab your graphing calculators. Does anybody need one? Who needs?
Least favorite unit.
I don't know, I'd have to think about that. I mean, it's math.
Do a little trick dance for us.
Least favorite. Okay. All right, here's the deal. Here's the deal. Guys, you have worked with degree measures before, right? Max was asking at the beginning of class, are we going to use protractors? You guys can visualize approximately what 48 degrees looks like, right? You have a general idea of what that looks like. Please don't think about degrees. You're not going to have to use protractors. What you were not told at that particular point is that degrees can be broken down into smaller units.
Like what?
Okay, so the words that we use to represent these smaller units, it gets, for some people I think it's confusing because they think that there's a connection between degrees and time, but there isn't. Okay, the smaller unit for degrees is minutes, and then the smaller degree for those minutes is seconds. The beauty is that it's just as we know There are 60 seconds in 1 minute, and there are 60 minutes in 1 degree. So no connection to time, except for, like, you already know that there's 60 seconds in a minute and 60 minutes in an hour, only now we're talking degrees. But, right, it's just a word, right? Same conversion. Thank you. That's a great way of putting it, Sebastian. Yes. Okay. You gotta have to learn a little bit about the notation. So you're used to the little degree symbol. I want you to notice how we would write 60 minutes. So minutes has a single hash mark. Okay. Seconds, if you notice, have that little double hash mark for seconds. So we can break these degrees down into smaller units, smaller parts. You're going to use those little symbols.
Can we write it though? Forget symbols.
What?
Like if I forget the symbols, can I just write 60 minutes?
No. A single hash mark, double hash mark. You can handle that, Max. All right. Here's the deal. There are 2 different ways in which these degree measures can be written, and we need to know. This is just basic foundational work for us for on down the road when we start working with some of these. In some instances, your degree measure could be written as a decimal, and for whatever reason, we may need to convert so that it's written as degrees, minutes, and seconds. So you need to understand how you can convert that way. Conversely, if it's written as degrees, minutes, and seconds, there might be some times when we need to rewrite it so that it's in decimal degrees. Okay? So I'm going to show you mathematically, because here's the deal. In some instances, you might have this graphing calculator, and in other instances, you don't. So if you have that graphing calculator, I'm going to show you. You're going to get it set on your calculator to have. If you don't, you have to know how to do this without your graphing calculator also. Okay, so here's the process. If you notice, if you're given something that's decimal degrees, notice what it says we're going to do. We're going to multiply the decimal portion by 60. So in other words, we take this 0.745 and we multiply it times 60. And the whole number part that we get for our answer, that's our minutes. Right? Look, we did the 0.745 times 60 and we got 44 point da da da. We're not worried about the point stuff yet. The 44 becomes our minutes. Okay? Then we're going to take this decimal part and we're going to multiply that times 60 again, and that becomes our seconds. Okay? So decimal part multiplied by 60. Take the decimal part that you get for that and multiply by 60 again. I want you to notice on this example, you can have a decimal as part of your answer for seconds. You can't have a decimal in the minutes. So grab your calculators. I'm going to give you an example. I'm just going to make this up, so I'm not sure how this is going to turn out, but whatever. 317.685 degrees. So let's try this. Just write this off to the side where you've got a little bit of space. 317.685 degrees. So what are we going to do first?
0.685 times 60.
There you go, Alicia. 0.685 times 60. Avery, where's your calculator?
Avery.
Okay, 0.685 times 60. What do we get, Campbell? Where is your calculator? I told you to get them out.
41.1. What is this calculator?
Okay, so we can start writing this out. We know we have 317 degrees. We're going to have 41 minutes.
6 seconds.
And then, we take this 0.1 and we multiply that by 60, and that gives us 6 seconds.
Why do we need that?
What are we learning?
Like, what are we trying to do?
We just converted. We had this degree measure that was in decimal degrees, and we've converted it so now it is in degrees, minutes, and
So
seconds.
are we multiplying the 317?
Because that's the full amount. That's the whole amount. We don't need to multiply that times anything. It's just the decimal part. It's the parts, the smaller parts that we have to figure out.
Multiplying it by 60 until it's not a decimal anymore?
Well, no, this could end up being a decimal.
It's a decimal.
The seconds might have a decimal. This is an that example.
So you keep multiplying it until you get down to seconds.
Correct. So you've multiplied by 60, you've multiplied by 60 again. So that's 3,600 altogether. All right. If we have degrees, minutes, seconds, and we need to convert so that it is in decimal degrees. So in some other instances, we have to convert the other direction here. Think about your conversion, right? We know that, whoops. All right, Ireland, get in highlighter mode. The 18 is minutes, so that's going to be out of 60. And then the 26 is seconds, so that's out of, if you think about it, 60 times 60, or this 3,600. Guys, you would just plug that straight into your calculator. Boom. Nice, right? So 124 point, da-da-da-da-da.
Wait,
Whatever the decimal
Then you
is.
gotta get that into seconds.
60 times 60.
So 18 over 60, the minutes are over 60, the seconds are out of 3,600.
What do you?
Okay?
Oh, we can just plug it into the calculator.
Plug
Oh,
18
yeah.
divided by 60 plus.
Oh, look who's listening. That's crazy.
Look at this guy.
Right. Max, did that answer your question?
No, what do we round it to usually?
Usually 3 or 4 places after the decimal. In Trig, it's for the most part, it's going to be 3 or 4 places after the decimal that we're going to go. Okay? All right, let's see. Yes, I do want you to see how you can do this on your graphing calculator if you have your graphing calculator, because a lot of times you will have it. You might have to do this occasionally by hand, but more often than not, you're going to have your graphing calculator.
I have my calculator.
So if you have, I'm just making this up, let's see, I don't know, 147.843 degrees. Okay?
Get to DMS.
I'm sorry, first thing is to check to make sure that your calculator is in degrees.
Okay,
50 minutes, 34.8 seconds.
Okay, so it's 147 degrees, 50 minutes, 34.8 seconds. Okay? Here's the beautiful thing about what you've just done. Your calculator is going to stay in this position in the catalog until you move it. And there's no reason to move it right now because that's what you need. So keep it right there, and then anytime you hit that little catalog key, the little book, you're going to be right there at the DMS that you need. Bravo. Okay. We need to be able to convert the other way, so I need to find out. Anybody need help with this? Are we good? Did everybody get that? Armand, did you get that now? Okay. Amira, did you get that?
I got it.
Okay. All right. If you have degrees, minutes, seconds, and you need to convert. So if we have something like 207 degrees,
All right, never again.
15 minutes, 28 seconds. Okay?
How do you write?
You have to be able to plug into that little
So we can use our calculator.
degrees, minutes, and seconds.
Only for certain.
Right? Okay, so here's where this is. Right next to the book,
I found it.
okay? It looks like that. It's what's referred to as the template key,
This is huge design.
but nobody remembers that word, and it's a boring word. So it kind of looks like a sideways smiley face. So if you hear me refer to the sideways smiley face key, that's the key I'm talking about. Kind of. Not exactly, but it's kind of a sideways smiley face key. So that's what I call it. So find your sideways smiley face key, arrow down to where you see that, highlight, type in, and once again,
207.
if you're leaving your calculator in that mode, until you move that to something else, it's going to stay there. So it's set.